Thank you all for joining us again for the Heidelberg Joint Astronomical Colloquium. This week, we're happy to introduce a local speaker, Gregory Green. Greg got his PhD from Harvard and then was a fellow at the Kavli Institute at Stanford. In 2020, he came to Heidelberg as a Sofia Kovalevskaya group leader at MPIA. And we're losing him in the next year to a professorship at Westlake University in Hangzhou, China. So we're very happy to be able to hear about what his group has been up to in their time here in Heidelberg before he leaves. So please take it away.
Good. Okay. So thank you for inviting me to give a talk. I'd like to talk to you about work that I've done on interstellar dust. And I'm going to talk about what we've learned about the nature of interstellar dust from Gaia, a large mission from the European Space Agency. I'm a group leader at the Max Planck Institute for Astronomy, as Catherine just said. And a lot of the work that I'm showing here, essentially all of it, was done in collaboration or led by Xiangyu Zhang, a student of mine. So I'll begin with just a little asking the question, what do we know about interstellar dust from the outset? And just as a very broad overview, interstellar space contains both gas in various forms, atomic, molecular, and dust, by which we mean small solid particles approximately less than 1 micron in size. What I'm showing here is actually not an interstellar dust grain. We have very, very few actual images of those types of grains, but this is an interplanetary dust grain from inside the solar system, which is much larger than a real dust grain. So if you look in interstellar space, you see, of course, stars, and then you see these very dark splotches, which are dust clouds. And the darkness comes from extinction. Dust scatters and absorbs light. The nature of what these clouds are is a more than 100-year-old problem. All the way back in I think it was around 1800, William Herschel was studying the distribution of stars throughout the galaxy, and he came across what's probably Rho Ophiuchi, and he said, "Hier ist wahrhaftig ein Loch im Himmel." Also, there is truly a hole in the heavens. And after that, there was a question about, are these regions where there are intrinsically no stars, or is something blocking the light? And so this was essentially answered about 100 years ago in an article in the Astrophysical Journal by E.E. Barnard, and has a very nice title, Some of the Dark Markings on the Sky and What They Suggest. And what he did in this article is he compared these dark nebulae with what they called back then light nebulae, or light nebulae, and he showed that they have, you can find for every dark nebula a light nebula that has a similar shape. And that sort of suggests that if these things are, if they look the same, they're probably somehow the same underlying phenomenon. And he said, well, maybe some of them are dark and some of them are light for some reason. Now, in the modern day, we know that these are reflection nebulae and nebulae that are not reflecting a large amount of light in the optical and therefore appear dark. And for this paper, which essentially discovered what dust clouds are, he only got 10 citations up till now, which is, I find sort of sad. But if you look him up, there's something very fun, which is that back then there was a magnate who was offering cash for any comet that you could find, and he discovered 8 of them, was able to buy a house for himself and his family. So we can't feel so bad for Barnard, I guess. Okay, so dust has different interactions with light. If we have a dust grain, and this is just a little cartoon where we have our star here and some telescope, like the Hubble Space Telescope over here, and we have a dust grain in the middle, there are different ways that dust can interact with light. One is absorption. Another is scattering. So these are, this is light that passes near the dust grain, and because of the wave nature of light, scatters. And then there's light that's transmitted that actually makes it towards our telescope. And because of the wavelength dependence of the scattering and absorption, more of the short wavelength light is absorbed and more of the long wavelength light is let through. And so this, in this example, this blue star might actually appear somewhat redder based on just the photons that reach our telescope. And so this is called reddening of background objects. And they also appear fainter because, of course, less light is reaching our telescope. The dust, in order to maintain some sort of thermal equilibrium, because it's absorbing light, has to emit, and it emits in the far infrared primarily. And so we have thermal radiation, which is another way that we can detect dust. So dust is really crucial for understanding many different phenomena in astronomy. One is star formation. These dust clouds are the sites of star formation, and so if you want to deal with star formation, you need to understand the dust that's in these clouds. It's important to planet formation. Of course, you could say that planets are sort of just very large dust grains, and so planets are built out of dust ultimately. It's important for the cosmic microwave background for cosmology because it's a foreground contaminant that can emit, and it can emit in the far infrared when you need to remove that component from the CMB. It also has polarized emission, which is a problem for finding the B mode of the CMB. If you wanted to understand distant galaxies based on their spectral energy distribution, you need to understand the dust properties of those galaxies. And so this is showing an example of the spectra of two different model galaxies, one that's dust-free and one that's dusty. And you can see that the SEDs are very, very different. Large-scale structure. So this is a map of the redshifts of galaxies. And in order to turn this into actual cosmology, you need to understand your selection function of which galaxies you observed. And that depends on the extinction and reddening of dust. And finally, of course, if you're interested in the ISM itself, the interstellar medium, then dust is a major component of the ISM. But despite the fact that dust is so important for many different areas of astronomy, we don't actually know that much about it. And so we can ask questions like, what is the chemical composition of dust? The precise chemical formula of all the different dust components is not known. How do dust properties vary across the galaxy? How do dust properties depend on the environment? And how does dust evolve over time? So we do know some things about these. We know sort of in broad strokes what the overall fraction of elements is inside the dust. And we know that, for example, as a function of the density of the ISM. And so we know how, for example, carbon abundance changes in the dust. But exactly what chemical formulae make up those dust grains, we don't know. So I'll talk first about how do we map where the dust is, and then I'll talk later about its properties. So there are a couple ways of mapping dust. One is far infrared emission. So the dust emits radiation in the far infrared. This is a picture from IRIS of three different channels of mid-infrared and far infrared dust emission. And if you model this emission as a function of frequency, you can model it as something like a modified blackbody, where you have some overall column density, some blackbody emission, and then because the dust has a finite grain size, it's less efficient at emitting in the far infrared at longer wavelengths. And so you have to have some sort of cutoff at large wavelengths. And so then you look at the SED of the dust, and you fit this model, and you get a column density out. And then you have some sort of calibration that takes you from this column density to your extinction, and you assume that there's some proportionality there, and you end up with a map of extinction across the sky. And you can do this using sources where you think you know the extinction or the true color of those sources. And so you end up with maps like this. This is a very widely used map. This is the Schlegel, Finkbeiner, and Davis map from 1998, which was originally made for cosmology, but which has been used for all sorts of things in astronomy. And what this tells you is at any location on the sky, what the integrated column density of the dust is, assuming that your modeling of the dust SED was correct. So there are some shortcomings of this type of map. One is that it's two-dimensional. We don't know how far away any of the dust is in this map. The other is that it's based on emission, but we're using it to correct for extinction. And so we'd really like to have a map that is actually based on the thing that we're trying to correct. And it makes assumptions about the dust temperature and emissivity. If our modified blackbody model is incorrect, then we could get the dust map wrong. And it suffers from contamination. There are external galaxies which also have dust in them, which also emit in the far infrared, and that gets into our dust map. There are also issues with zodiacal light from our own solar system and from the cosmic infrared background. And so we really want a better map that's three-dimensional, so we know the distance to the dust, and which is based on extinction. And that will be much better for actually correcting for extinction in the galaxy. So the basic way that we do this is we assume that the sun is here, and we observe stars surrounding the sun, and then there are various dust clouds. And so, for example, there could be a dust cloud here, and everything behind the dust cloud appears redder and fainter. And then if we take one sightline, we want to map the extinction as a function of distance along this one sightline. And we could just look at the colors of stars and how they change along that sightline. But what makes this complicated is that the stars themselves have different intrinsic colors. For example, they have different temperatures. And so you actually have some scatter in the colors of stars at any given location, and they're not all the same color. And so you actually have to model both the intrinsic type of the stars, so for example, their temperature, and their distance, and the extinction. And so you can do this along a sightline. For example, let's take this one sightline here, and we're going to measure distance versus extinction. And we take all the data that we have on one star, could be spectroscopy or photometry or maybe a parallax, and we use all that data to get an estimate of its distance and extinction. And that will be a probabilistic estimate. It won't be a perfect estimate, so we'll have some uncertainty on that estimate. And then we do that for the next star along this line of sight, and we keep on doing that for all the stars, and eventually you can see some sort of relation of how extinction is increasing with distance. And then we try to draw some sort of plausible curve through that relation that's showing you how extinction changes with distance. And you can see there's a big jump in extinction at one distance, and that would mean that there's a dust cloud there. And if you do that in a probabilistic way, you actually have a family of possible extinction versus distance relations along this one line of sight. And that's telling you the possible distances to this cloud and the possible Coulomb densities of this cloud. So we do that for millions of sightlines across the Milky Way, and we end up with maps like this. So this is showing you the dust within 250 parsecs. And then we can step out in distance and see dust in different distance slices across the sky. And so we're stepping farther out. Then we can also take a top-down view. You may notice there's a very big difference between the inner part of this map and the outer parts. This is the region nearest to the sun where we have the best maps, and then farther out, the maps are not as good. And then we can do fun things like make videos of what the dust would look like if you had a camera that could orbit the sun. And so this is looking away from the galactic center. And people here who know the map of the ISM will recognize this is Orion. This is Lambda Orionis, California, Perseus. All these things have names. And behind there, you're seeing the plane of the Milky Way. So, okay, we can map dust, and we can map how much of it there is across the sky, but what about dust properties? And so these maps are telling us the density, but they're not telling us, for example, what is the composition of the dust and how is it changing. And we can get more evidence of the composition of dust from its interaction with light. So we can look at, for example, the wavelength dependence of extinction, or how extinction is polarized, or X-ray scattering off the dust grains, or the emission spectrum of the dust and how that varies, and many other observables. And I'll focus in most of the rest of this talk on the wavelength dependence of the extinction. So in order to predict the wavelength dependence of extinction, with some sort of physical model, we need to model a few different things. One of them is we need to have a model of the dust grain composition. So does it contain silicates, metal oxides, carbonaceous grains, hydrocarbons? We had to make a whole list of things that we're putting into the dust. And that gives us a dielectric function of the dust. And then we need to know the distribution of grain sizes and geometries. For example, are the grains prolate, oblate, spherical? How porous are they? Are they just very compact, or do they have voids inside them? And that then gives us, these two things combined, give us the scattering and absorption cross sections as a function of wavelength of the dust population. And that's calculated using Mie theory. And so this tells us the extinction cross-section as a function of grain size and wavelength. And we have a geometric cross-section, which is just how large the grain is. That's this term. But then we also have an extinction efficiency, which is telling us how efficiently can the grain absorb light of various wavelengths. And that you need to calculate using electrodynamics. And so these are efficiencies as a function of wavelength of grains of different sizes. And so you can see generally the smallest grains, once you go to some wavelength which is much larger than the grain size, the efficiency drops. And as the grains get larger, that wavelength at which the efficiency drops pushes out to longer wavelength. Basically, larger grains are more effective at absorbing longer wavelengths. And then we have various specific transitions in these molecules, which allow us to absorb at very specific bands. So for example, there's a silicon-oxygen stretch mode, which is around 9.7 microns, which you can see here. And there are various other modes that tell us, for example, that there are silicates in the ISM. But what precisely these silicates are is more difficult to determine. We also know that there is some sort of hydrocarbons because there's a CH stretch mode. So we have some information here already about that what sort of classes of components can go into these dust grains. And here I've made some very specific choices. I've said 20% porosity, no metallic iron, a certain axis ratio. But if you change these properties, then these curves change. And if you now assume a grain size distribution, so this is a very famous a classic grain size distribution. It says the number of grains as a function of wavelength, or as a function of grain size, goes as a to the negative 3.5, where a is the grain size, over some range of sizes. If you plug that into your scattering efficiencies and calculate what the extinction should be, you can calculate, for example, for some silicate grain population, what the extinction as a function of wavelength should be. And so this is one particular model of what the silicate extinction should be as a function of wavelength. So if you put a couple different components into your, not just silicates, but other components into your extinction curve model, you get something more realistic that looks like this. What I'm going to call the extinction curve, so I'm going to call this wavelength versus extinction, the extinction curve in the rest of the talk. And you can see there are a couple prominent features here. One is this bump at 2175 angstroms in the UV. Then the slope of the extinction curve in the optical is parameterized by this variable called RV. It's basically the inverse slope between B and V bands in the visible. So the inverse slope of the extinction curve in the visible. And the basic way that this works is if you have a very small grain size distribution, so where most of the grains are very small, then the scattering efficiency drops very rapidly as a function of wavelength, and you have a very steep extinction curve. And that corresponds to a low RV. So you can think of low RV as being small grains. And if the grains become much larger, then they become more efficient at scattering and absorbing at large wavelengths, and you have a high RV. So high RV you can think of as large grains. So most of the previous work with measuring the extinction curve has been done with hundreds of hot OB stars. These stars are used because when you're measuring the extinction, you're not necessarily interested in the properties of the background stars. You're using them just as some sort of background light to measure the dust. And so you want something that's as bright as possible. And it helps if you're interested in the ultraviolet extinction to have something that's as bright as possible in the ultraviolet. And that means having young, hot OB stars. There are not that many of them, and there's limited time on facilities like HST. And so there have been several hundreds of OB stars measured in the Milky Way where we have these measurements of the extinction curve. You can already see in this spectrum that the 2175 feature in this spectrum is really obvious. But then, of course, you also have to model the stellar SED as sort of a nuisance. So if you do this for a star very carefully, you get an extinction curve like this. This is on the x-axis here, inverse wavelength. For some reason, that's the common way of plotting this in the extinction community. So short wavelengths over here, long wavelengths over here. This is a 2175 angstrom bump. You can see various individual features. There are also these features called diffuse interstellar bands. These are specific bands that are quite broad, but which are almost all of them of unknown origin, and I'll get back to that briefly later in the talk. Okay, so we wanted to go beyond just measuring the extinction curve with hundreds of stars, and so we turned to a relatively new data set, which is Gaia. So people here might think of Gaia as primarily an astrometric mission. Gaia is most well known for the fact that it's measured the parallaxes of over 1 billion stars. But Gaia has actually measured also spectrophotometry for hundreds of millions of stars, and it disperses the light of each star along some axis, and then you get a spectrum of every single star over the sky down to some magnitude. And the stars are potentially overlapping, but then if you scan over the sky at different angles, there are different overlaps in every spectrum, and you can actually disentangle the different spectra. I'm cheating here a little bit with this very beautiful image. This is actually from Euclid, but it's a similar idea. So these are very low resolution spectra, R of something like 50 to 160. We might even call them spectrophotometry. It's somewhere between spectra and photometry. The wavelength range is primarily optical. It goes a little bit into the near infrared. And these are flux calibrated spectra of 220 million stars so far. So it's a huge number of stars compared to other spectroscopic surveys. This is what the individual spectra actually look like. They're called BPRP because there's a blue photometer and a red photometer, and so you get two spectra, which then get combined into one. And these little smudges then get turned into spectra that look like this. So wavelength, flux, and you can see these are very rough spectra. The strengths and limitations of these spectra are, well, one limitation is that only the broadest lines will be resolved. So we're not going to get very precise, very fine lines from these spectra. But the overall shape of the spectrum is well preserved because these are flux calibrated. And these are good enough to estimate temperature, metallicity, and extinction at fairly high precision compared to photometry. And another really nice thing is that these cover the entire sky. So we can really measure extinction across the entire sky with these spectra. So next I'll discuss how we actually model the extinction curve using these XP spectra. These are very low resolution spectra, so we had to approach them in a different, the modeling techniques that we had to use for them are different from what has been used in the past for high resolution spectra. So we have these low resolution spectra, and we cross-match them with a higher resolution ground-based survey, LaMost. This is has an R of about 1800, and from these spectra, we actually get stellar types, so T-effective, metallicity, log surface gravity, and that will be our sort of ground truth for learning what XP spectra look like. Now, you could just take some sort of machine learning model and try to go directly from the spectra to the stellar parameters using some sort of regression technique. And that's been done by several different groups, but we favored the opposite direction, which is going from the ground truth and predicting what the spectra look like. And then we can use Bayesian inference to actually get a probabilistic estimate of the stellar type from our forward model. So we train this model using a cross-match of about, we have a cross-match of about 2.4 million stars that we can train this model with. So the forward model of our stellar spectrum is going to predict what the flux is like, looks like as a function of wavelength. And it's going to depend on several parameters. One is the type of the star, so its intrinsic parameters. One is the distance or the parallax. We also need to have some dust parameters. We need to know the amount of dust and then the RV of the dust. And the way that we structure our model is that we shove everything about stellar physics into a neural network. So this neural network takes in the stellar type, and it has a bunch of neural network weights, and it outputs as a function of wavelength the intrinsic spectrum of the star. Then we put in the fact that we know that there's an inverse square law, so flux should drop as the square of the distance. And we put in the fact that there is such a thing as dust extinction, which should depend on wavelength. It should depend on the amount of, it should scale with the amount of dust. And then there should be some wavelength dependence that depends on wavelength and RV. And we learn, everything in red here is learned. So we learn what intrinsic spectra look like. We learn what the extinction curve looks like. And then we also use our measurements from LaMost, Gaia, and three-dimensional dust maps to have initial guesses of what the stellar parameters are. And then we update those parameters as we train. So we actually end up learning everything globally. We learn both the stellar parameters and the global model at the same time. So if you train this model, and I just want to point out as well that this model, it reflects the physics of F lambda. So we know that there's an intrinsic spectrum, the inverse square law, and dust extinction. So if we train this with 2.4 million stars, we get a set of models that look like this. This is just an example. These are solar metallicity stars as a function of effective temperature. And so these are different spectra. And you can see that we are recovering, or our model learns the fact that there are hydrogen lines and where they are and how they depend on temperature. It also learns that there are metal lines and how they depend on temperature and also how they depend on metallicity. And so we're recovering out of this some realistic set of stellar spectra. We also learn an extinction curve and how it depends on RV. So again, red here means, well, canonically would mean smaller grains. Blue would typically mean larger grains. And you can see how the slope of the extinction curve changes with RV. We also see these bumps and wiggles in the extinction curve, and I'll get back to that later. So now we use our forward model to infer the parameters of stars and dust. And so we apply our model to XP spectra with near-infrared photometry from WISE and 2MASS and Gaia parallaxes to infer the parameters of all 220 million stars that have XP spectra. And I just want to emphasize that we're not using LaMost for this parameter inference. So LaMost is only used to learn the model, but it's not used afterwards to learn the stellar parameters. And if we then remove all the stars that don't pass our quality cuts, like chi-squared per degree of freedom, we end up with 130 million measurements with high quality RV determinations. And so we can compare this with previous catalogs of RV determinations. So this is one of the largest catalogs of OB star RVs, and I'm showing you over the sky what they look like. The galactic center would be here. The gray contour in the background is showing you the total dust column density, and then every dot here is a star with an RV measurement. This is a measurement of RV for about 37,000 stars, done by Eddie Schlafly in 2016. I think he was actually at MPIA at the time, if I remember correctly. And this is using apogee spectra. And so this is the apogee footprint from back then. And this is a more recent measurement using LaMost. And so this is 1 million RV measurements from LaMost by a different Zhang. This is Ruoyi Zhang in Beijing. And then this is our measurement of 130 million RV determinations across the sky. This is just showing you the average RV across the sky, but we actually have this as a function of distance as well. And so I can show you in the galactic plane, these are the OB stars. This is the sun in the galactic center. These are the stars that Eddie Schlafly measured. These are the stars from LaMost. Then these are our determinations. You can see that we had this, we call them sometimes finger of God effect. And that's because one dust cloud in the foreground affects all the stars behind it. And so that's why you see this streaking effect here. So this is orders of magnitude more RV measurements than have ever been available before. If we compare to just a few years ago when we had only apogee, there were 37,000 measurements. Now we have 130 million measurements. Or 2 years ago we had 1 million measurements. Now we have 130 million. And so I'm going to show you first results that we have for a variation of RV throughout the galaxy. So this is the first time that we really have, in a dense sense, a high resolution map of how RV varies in 3 dimensions throughout the galaxy. So this is the galactic plane, and this is showing you the integrated, sort of the average amount of, the average RV of all stars along line of sight as a function of position in the galaxy. And then we can zoom in on different clouds, for example, Rho Ophiuchus, and we can see that it has typically very high RV. Or we can zoom in on Taurus and see that it has low RV, except in these very dense regions where we start to run out of stars, but you can see that there are these little knots with higher RV. Or in Orion, the outskirts of Orion have low RV. But then once we get right into the nebula, we have these regions that have very high RV. And so this is showing you us that there are variations both on large scales in RV, but also on very small scales. One trend that we found fairly consistently across many different clouds was that as density increases in the cloud on the x-axis here, RV tends to first decrease and then increase. And this is actually across a few different clouds. And this was somewhat surprising to us. Previously, we had thought that as grains grow through coagulation in dense regions, the grains should stick together and form larger grains, RV should increase. But we see first at relatively low densities, this decrease. So that was somewhat puzzling to us. Some evidence about what this might be caused by you can get from looking at the RV in the galactic plane. So this is the sun is here. The galactic center would be off to the right. These are the densities of clouds in the galactic plane. We can then put the RV on top of this, and then we can put the O stars on top of this. And the O stars are tracing recent star formation. And it turns out that there's a correlation between recent star formation and high RV throughout the galactic plane. And so this suggests some sort of correlation between star formation and high RV. We see the same thing in the Magellanic Clouds, where regions of intense star formation like 30 Doradus also have high RV. So this is the first time we can actually see the dust properties, or at least the extinction curve of the dust throughout the Milky Way in 3 dimensions. And we have already a few results. One is the U-shaped relationship between density and RV, and the other is star formation, perhaps UV radiation are correlated with high RV. And so this is just a very large empirical data set that can be used to further study the chemistry of the interstellar medium. So I'll now tell you one proposed mechanism of some of these RV variations that we've seen. So there's a class of hydrocarbons called polycyclic aromatic hydrocarbons. These are essentially fused benzene rings, so rings of 6 carbon atoms with hydrogen bonds on the outside. And sometimes they have various side groups. So these are not all perfect PAHs, but there are essentially an infinite variety of PAHs with different geometries and different side groups on them. And these are very abundant in the interstellar medium. And they're one of the prime candidates for the 2175 angstrom feature, because there's a particular electronic transition that very generically occurs in these types of molecules, which produces a transition in the UV. And so they're one of the primary candidates for the carrier of this bump. If you take a particular dust model, for example, we're taking the Hensleyan drain dust model, it consists of different components. One is this large silicate population, which contributes some extinction, especially at large wavelengths. And then it consists of a PAH component, which contributes the bump, the 2175 angstrom bump. And if we take this PAH population and increase its density, it makes the bump, of course, stronger, but it also makes the optical extinction a little bit steeper, because the bump has a long tail into the optical. That makes the optical extinction steeper. So it turns out that if you look at what the RV of this extinction curve is as we increase the amount of PAHs, you can see that RV is going down as we increase the amount of PAHs, just because of the long tail of this 2175 angstrom feature into the optical. And so this means that if PAHs are growing in the interstellar medium in these intermediate density environments, we would get a stronger 2175 angstrom bump, deeper optical extinction, and lower RV. That's one way of explaining what the trend that we're seeing. Now, you might also try to, so then I'll just go back a little bit. This would also explain the high RV in star-forming regions, because you have intense UV radiation in these regions, which should destroy PAHs, which would then lead to higher RV because you're getting rid of the 2175 angstrom bump. So you might ask the question, maybe accretion onto silicates is actually causing the phenomenon that we see. And so in the interstellar medium, you should have accretion from the gas phase of metals onto grains. By metals here, I mean what astronomers call metals, anything heavier than helium. And that would then alter the grain size distribution. And so if we take a typical MRN sort of canonical grain size distribution, which I'm going to show is flat here. So I've taken out the a to the 3.5 component here. So if it's flat, it's an MRN distribution. And this is grain size versus the abundance. As you accrete more and more material into grains, you tilt the grain size distribution, and actually RV tends to decrease. This is somewhat counterintuitive because all the grains are getting larger, but RV is still decreasing. And the reason for that is the way that the grains are getting larger is actually making the surface area of the small grains increase more quickly than the large grains. And so the small grains come to dominate, and you get an extinction curve which should have lower RV. However, when you actually work out the amount of material you need to accrete onto the silicates in order to have this effect, it's orders of magnitude more material than actually exists in the ISM. And so we believe that this is not really a viable mechanism for explaining the trends in RV that we see. We also have additional empirical evidence that there is a correlation between, or rather an anti-correlation between RV and the PAH abundance. For example, if you look at the LMC, there are maps from the infrared of the PAH mass fraction in the dust. And you can see, for example, Doratus has very low PAH fraction. Essentially, the pHs have all been destroyed by the UV radiation field. And they also have, these regions also have high RV. And so there's a correlation across not only the LMC, but many or several different clouds that we've studied in the Milky Way, where you see as the PAH fraction increases, RV decreases. But we think that this theory, there needs to be some follow-up at other wavelengths to try to test this theory. If we were to look in the UV, we could directly compare the 2175 angstrom bump to the RV that we see and see that if that is actually behaving in the way that this hypothesis says it should behave. We can also look in the near infrared and look for a particular feature at 3.3 microns. And there are also numerous pH emission features in the mid-infrared. And so, for example, in the mid-infrared, we could test whether or not the pHs themselves are actually growing based on the ratios of different features and see whether or not our hypothesis is correct. Okay, and so finally, I'd like to talk about going beyond RV. So up till now, I've just talked about the extinction curve is depending on only one parameter, the overall slope, and the optical, which is parameterized by RV. But is there information beyond RV in the extinction curve, or is everything described by just this slope? And so we know that in the UV, the answer is no. These are various UV extinction curves for different OB stars. And you can just see that there's more going on here than just some sort of slope. The strength of the 2175 angstrom bump is changing. The slope of this far UV rise is changing. And it's not all perfectly correlated with RV in the optical. So what about in the optical? Is there more than just RV in the optical? And so we try to answer this question by looking at empirical extinction curves for individual stars. So far I've told you that we've estimated the RV of every star for 130 million stars using XP, but we can actually go back to our high quality observations and try to get an empirical extinction curve as a function of wavelength. And the way this works is we begin with our observed extinction curve, which has some uncertainty on it. And then we actually look at our model of its stellar type. And so this is then given our model of the stellar type, this is the intrinsic flux of the star. And the difference between these two things, the observed flux versus the intrinsic flux, is the extinction. And so we look at that extinction as a function of wavelength. And we compare that to our model that depends only on RV. So this is the best fitting RV model to that particular extinction curve. And we can look at the differences between that model and the RV. And you can see there are all these little bumps and wiggles. And the question is, are those significant, or are those just problems with the data? So we approach this by looking at an ensemble of many different extinction curves. So on the left are the raw extinction curves of different stars. We then normalize them at some wavelength. So we're only looking at the shape of the extinction curve. And then we look at the difference of that shape versus some nominal average extinction curve. And so that's the thing on the right. And you can see that there's a trend. So every extinction curve is colored by its RV. So from blue to red, there's a trend here. You can see that RV is the dominant variable here, but it doesn't explain everything. And so we decompose these extinction curve shapes, which I'm calling this little r of lambda, into different coefficients and bases. So we're going to try to explain all of them using 16 different basis functions that each have different shape as a function of wavelength. And every star will then have 16 components that describe what its extinction curve is. So we learn the bases and the coefficients for every star, and we come up with a set of bases. And what I'm showing you here on the top row is the first most significant basis, how it depends on wavelength. So this is the deviation from the mean extinction curve as a function of wavelength. And then I'm showing you the mean strength of this basis across the sky. And this first basis is actually just RV. So this is changing the short versus long wavelength extinction of these stars. And this is essentially just an RV map. But then we have higher order components. So this is the first higher order component, and it has some different wavelength response, and it has a different spatial pattern on the sky. And we can go to the higher order components. So I'm showing you the second and third higher order components. This is their wavelength dependence, and then the response on the sky. And we can then zoom in and see for these different components on the same part of the sky, what is the pattern on the sky of these components. This is RV, then these are the higher order components. And the low order components, if you just look at them visually, look like filaments and clouds. And so we think that they look more dust-like. The higher order components look more what I would say Gaia-like, in that you see these arcs, and you also see this checkerboard pattern, which is very typical of the systematic calibration problems in Gaia XP spectra. So the higher order components are probably picking up actually systematic calibration issues in the Gaia spectra, but we think that the lower order components are more true to the actual extinction curve. And in the paper, we do some more advanced tests of this by, for example, splitting on a stellar type and showing that these low order extinction curve components don't depend on what type of star you're looking at. So we identified in these variations a new broad feature in the extinction curve at about 850 nanometers. It's actually centered on 848 nanometers, but I'll just call it the 850 nanometer feature from now on. And it's very, very broad, much broader than any DIB. And we also confirmed a previous discovery by Mais Apellinis et al. From 2021 of a narrower, well, still very broad feature, but somewhat narrower feature at approximately 770 nanometers. And the properties that we measured of this feature are very precisely the same, so the equivalent width and the central wavelength as Mais Apellinis. So it gives us some confidence that we're measuring these features correctly. And then this new feature we're adding to the catalog of known optical features. We can actually map the strength of these different features across the sky using our extinction curves. And so just to orient you, here are some famous clouds. The galactic center is here. This is the galactic plane. And then the top row is the equivalent width of this 770 nanometer feature that we confirmed. And then this is the equivalent width of the 850 nanometer feature. And you can see that the variations are correlated with one another, but not exactly the same. So if we zoom in on one part of the sky, near Rho Fucus, we can plot RV. So this B naught is essentially RV. And then these equivalent widths of these two features. And we can then select some part of the sky, which I'll call the north region, so just north of Rho Fucus. And we can then look at what is the average extinction curve in that part of the sky. So as a function of wavelength, what is the average shape of the extinction curve? Now I've subtracted out the average extinction curve, which is why it is increasing with wavelength. And we can then compare that with other lines of sight across the entire sky, which have the same RV. And so you can see that this extinction curve in this region of the sky is not well described by the average extinction curve for other regions with the same RV. And we can select a different region, which I'll call the east region, and see its average extinction curve. And then we can compare that with other regions which have the same, across the entire sky, which have the same average RV. And you can see that, for example, in this region, which is called the very broad structure, which is a known feature in the extinction curve, that this broad structure has a different strength in this region than on average. And so the basic take-home message here is that RV does not explain all the variations in the extinction curve in the Milky Way. All the features that we found are of unknown origin. So both the 770 nanometer feature and the 850 nanometer feature, we don't know what the chemical carrier of these features is. But we know that they correlate with one another and that they correlate with RV. So this B0 is essentially RV. And then you can see correlation plots of the different features with each other. And there are some fairly strong correlations. And they also appear to correlate with the strength and the shape of diffuse interstellar bands. So diffuse interstellar bands are these bands which have been known about for many decades, which I think there are over 500 bands that are known now, and only 4 or 5 of them have a known carrier, which is a buckyball C60 plus. But the rest of them are of unknown chemical origin, and we found that several of them are correlated with the strength of our extinction curve features. So what I'm showing you here in the top row is the average strength of this 15,272 nanometer diffuse interstellar band. That's its average profile. And then this is how the profile changes as you change RV. You can see the profile becomes somewhat wider with RV. And then the profile also changes in shape as you change these higher order components of the extinction curve. So the extinction curve is not only changing with the grain size distribution, but there also appear to be some chemical variations that are correlated with the properties of the diffuse interstellar bands, which also are correlated with the extinction curve variations. Finally, we can look at residuals and the feature strengths. What this means is there are correlations between, for example, the 770 nanometer feature and RV. And if we subtract that correlation and look at the residuals from that correlation across the entire sky, we can see that Rho Fucus is an outlier. And Rho Fucus is one of the nearest large star-forming regions. It should have a very strong UV radiation field, and so this could perhaps say something about the stability of the carrier of this feature as the UV radiation increases. So just in summary, what have we learned about dust from Gaia? We still don't know its detailed composition. So I can't tell you exactly, dust has this chemical formula and this exact grain size distribution. But we can map the extinction curve throughout the galaxy, so we have a lot more empirical information for modelers to work on now. We know that, well, I wouldn't say we know, but we have evidence that a significant fraction of RV variation is probably driven by PAHs. Not all of it. Grain size distribution also plays a role. But we think that PAHs are maybe playing a larger role than was previously thought. And we've also learned that the optical extinction curve has more degrees of freedom than just the overall slope, than the overall RV, and that these are correlated with the chemistry of the ISM. For example, they're correlated with DIBs. And so with that, I'm happy to take questions.
All right, I'll open the floor to questions, especially from students and postdocs. No students and postdocs? Understood it all.
Hello, I was just wondering where you map this like 3D structure of the dust. Can you also fit or set a free parameter like the dust opacity? Like do you have information on what the dust opacity is in different regions of the galaxy, or like how much it varies? I don't know if that's.
You mean the dust opacity in the infrared, or?
Yeah, in the infrared.
So there have been attempts to combine the three-dimensional maps with the two-dimensional information that we have from far infrared emission to produce a three-dimensional map of the temperature of the dust, for example. So you fit some sort of model the temperature and how that should change the emission spectrum. So that sort of work has been done before. What I've been doing mostly is measuring essentially the optical opacity which you could call the extinction curve.
Okay. Okay.
Another question up here.
I have a question to the infrared follow-up observations. Have you checked out that with ALMA observations of dust, if you look at the Rayleigh-Jeans limit of the thermal emission, have you checked out this, whether it is somehow correlated to this extinction curve you measured? And the second question is, what about the Sophia archive? Have you looked at dust in the Sophia archive?
The answer to no, both is no, but it does sound like very good ideas for follow-up work. I'd be happy to talk to you afterwards about that.
Questions?
We have already some interstellar grains which were collected by the Stardust space probe, and we know a little bit of the chemistry. Have you compared this chemistry, and is this compatible with your models?
So I don't actually model the composition of dust grains. I was using as an example the Hensley and Drain models. I think there's some sort of tension between them where the if I understand correctly, the stardust grains were very well separated in terms of silicates versus carbonaceous material, if I remember correctly. And I think it's a challenge for the models because, but this is not really my exact field, so I don't want to say too much there.
Questions?
So I had a question. Basically, are we even close to finding out partially the chemical composition of interstellar dust, and how far along are we in this process?
I hope so, but this is, as I said, it's a 100-year-old problem, and we've made some progress. We know some, like the rough composition, overall what elements go into the dust, and roughly what proportion. But in terms of the exact chemical composition, it's actually very complicated to go from you could go from a precise model of the dust, what exact chemical components are in it, and then work out the dielectric functions and the grain size distribution and turn that into a model of the extinction curve and the polarization and all these other observables. But the problem is that the model space, the set of possible things that dust could be, is so large that there are many, many different possible models that you can make. And it's very hard to pin down, exactly this model is correct. The best way to do that is to have many different observables that make predictions about different things. For example, the extinction curve, how polarization depends on, say, the magnetic field or on wavelength, X-ray scattering. So there are different things you can try to look at and try to find a model that fits all the various types of observables. But I think that the fact that we can measure the extinction curve now throughout the entire galaxy is, I think, going to give the modelers a lot more to work with.
You have shown how much beautiful progress one can make with Gaia, and it's very low resolution spectra. There's now a new mission out, Spherics, which will take very low resolution spectra of everything from 1 to 5 micron. What is that a useful wavelength region for this field?
Yes, I think Spherics will be really great for dust. One thing is that it's measuring the 3.3 micron PAH feature in the near infrared. The other thing is that we could potentially get stellar extinction curves from Spherics. It's essentially Gaia goes out to 1 micron about. So it could extend all this work to 5 microns.
Greg, this is beautiful data and really cool analysis of this treasure trove of information. I'm wondering about how much mass you are losing or missing in this approach. I mean, from the Edenhofer map, which I looked at quite a bit lately, we see it saturates at about 25 to 30 particles per cubic centimeters. And if I compare, for instance, the mass in the Edenhofer map along sidelines to Taurus or Perseus or some of the known regions with the dust emission map, Herschel or also Planck, at the high column density sideline, it misses most of the mass, whereas at the other side, at the low column density sidelines, it actually retrieves more mass than any of Herschel and Planck. So I was wondering what to do with this information. How much mass is there and which map can I trust most? And have you done the cross correlation?
Yeah, so you mean these very dense regions we're essentially running out of stars because
exactly, yes.
We're limited to about 17th magnitude in Gaia G-band. So if you want to go deeper, one way is to go into the infrared, which SphereX will help with. And another way is to use photometry. But then you're losing some of the precision of these Gaia XP spectra. So you're going from having tens of, maybe R of 50 to 150 to having R of like 5 or something in your spectral resolution. So one thing I want to do is extend these models to work with photometry as well, and just see how well we can constrain RV there. In terms of how much mass we're picking up, I haven't compared mass estimates from this to mass estimates, for example, from Planck. And I guess that would depend on your assumptions about the grain size distribution and how it varies with RV, right? Because you need to have the conversion.
Sure, but you also need to make assumptions. And I mean, for me, a theorist, I want physical units, right? I want mass density or column densities in H atoms per cubic centimeters. And you provide, and Edenhofer and the Herschel guys and the Planck guys provide conversion factors. And so I was wondering what I do in the case, and they almost never do, when they disagree. And they disagree by factors of a few in some sidelines. And so it would be super useful to have someone doing a cross correlation that can someone like me help in converting these to.
I think I can explain a little bit why they could have disagreed to such a large extent. The thing that they'll all agree on fairly well is the integrated extinction. So if you integrate along the integrated extinction. Yeah, but if you look at the density though, for example, this inside here, this is the Edenhofer et al. Map, which has much higher distance resolution than the other maps. And so if you compare that to this map, all the dust is getting smeared along the line of sight, which will decrease the densities that you're going to infer. And so I think you want to go more with a map like this, which has better distance resolution if you're interested in dust densities. But even there, these maps are based on Gaia, and so they'll run out in the very dense regions. They just won't pick it up at all. Yeah, so there's a huge amount of, these will be biased low in density in dense regions. Yeah.
Thank you. So do you think dust properties can vary fundamentally or qualitatively from the Milky Way to other galaxies? For example, early type galaxies, because your results are based on the Milky Way and the Magellanic Clouds. Or to put it in another way, do we learn something new and important from looking at external galaxies or even higher redshift?
So the short answer is yes, they should vary quite a bit. So the small Magellanic Cloud, for example, has quite a different dust extinction curve. It's steeper and doesn't have a prominent 2175 angstrom bump. So there's obviously chemical variation. It could be dependent on metallicity, because the SMC is at lower metallicity. But it also could depend on, so at very high redshift, for example, the mechanisms of dust production are different. When you go to very early times, it should be supernovae, which are the predominant way of producing dust. And then at later times, when there's enough metallicity built up in the ISM, there are processes in the ISM of grain growth and destruction that you kind of reach an equilibrium where the inputs from supernovae and AGB stars are not as important. So over cosmic time, what is actually producing dust is different. And so there should also be differences in populations. There have been some findings recently of at high redshift of about 7, the 2175 angstrom bump. And it's still a question of where that comes from, because it's too early for PAHs to have formed from the atmospheres of AGB stars. So yeah, it's an open question.
Thank you for the very interesting talk. So you focused mostly on the sort of spectral information from Gaia, but of course there's a lot of other information there. And I wonder if you have actually looked at the proper motions, for example, and if there's any correlations of the dust properties or your extinction properties. Because I could imagine, you don't expect it initially, but I could imagine that, for example, dynamically hot regions where some activity has gone with stellar collisions might be stirring up the dust there and changing the properties in the surrounding cloud.
You mean the stellar proper motions?
Yes.
I haven't thought about this at all.
I mean, it just something to consider is to look, since all of these data are already available, just see if there are correlations where you might not expect them.
I mean, so right now I'm most focused on correlations in ISM properties, so things like the interstellar radiation field and its strength. If you can, for example, I showed the correlation between OB stars, which already tells you that there should be some correlation between star formation and dust properties. And then there are other groups that are working on, for example, mapping out the UV interstellar radiation field throughout the galaxy, which involves ray tracing through dust maps and so on. So those are the types of things I think are most promising right now. But I haven't thought about stellar dynamics and how it would respond to this.
All right. I don't see any more questions. So then let's thank Greg again.